Yo guys, it is I, Little Ting, and today I'm going to be reacting to Physics Revision playlist. Let's go. Yo, it's density. Free lesson. Yo, you should really get this guy.
Hi, welcome back to freesciencelessons.co.uk. By the end of this video, you should be able to draw diagrams to model the differences in the arrangement of particles between solids, liquids, and gases.
Bro.
You should then be able to calculate the density of material, and finally, you should be able to explain the differences in density between different states of matter.
Pretty interesting,
Now, there
bro.
are three common states of matter,
I
and
think
these are
that this
solids,
guy's
liquids, and gases. We're going to start by looking at how the particles are
This guy's
arranged
so
in these
cool.
three states. Let's start with
Ignore the
solids.
noise in the background, that's just the sound of me. Ignore any of this, ignore that. Spooky. Ooh.
I'm showing you the arrangement of particles in a solid here. In a solid, the particles are very close together, and they're arranged in a regular pattern. Particles in a solid vibrate, but they do not move from place to place. Here's the arrangement of particles in a liquid.
They're close
in a
together.
liquid, the particles are still close together, but they're not arranged in a regular pattern. In fact, the particles in a liquid can move around each other.
They're free to move, they have energy.
This shows the arrangement of particles in a gas.
They're not
You
close
can
to
see
each
that the
other.
particles are very far apart, and they're not arranged in any pattern.
No
in a
pattern
gas,
at all.
the particles are moving very rapidly. Now in the exam, you could be asked to draw the arrangement of particles in solids, liquids, and gases, so it's really important that you learn them.
No.
Okay, we're going to take a look now at density. The density of material tells us the mass for a given volume. Now that sounds tricky, but the idea is relatively straightforward. I'm showing you here a brick and a polystyrene block.
Volume divided by mass.
The brick has a high density. It has lots of mass packed into its volume. The polystyrene block has a low density. That's because it's got a lower mass packed into its volume.
True though.
We can calculate density using this equation.
Yo, it's mass divided by volume. I told you, bro. I told you. It equals to
the
density,
equals the mass in kilograms divided by the volume in meters cubed. The unit of density is kilograms per meter cubed. And here's a triangle if you prefer to use these. Now, you're not given this equation in the exam, so it's important that you learn it.
Yes.
Here's a question for you to try. A block of wood has a mass of 150 kilograms and a volume of 0.3 meters cubed. Calculate the density.
Yo, let's get a calculator up. No, not calendar, calculator. No, just calculator. Yo, so it's 150 divided by 0.3. Skitty up, here we go. Obama ball, Travis ball, Obama likes men. Is it going to be 500?
Pause the video and try this yourself. Okay, so the density equals the mass divided by the volume. The mass is 150 kilograms and the volume is 0.3 meters cubed. Putting these into the equation gives us a density of 500 kilograms per meter cubed.
I got it right.
Now we can use the particle models that we saw earlier to explain the density of different materials. Solids usually have a very high density.
Very high.
Because the particles are packed closely together, solids have a lot of mass for their volume.
They have a lot of mass for that.
Liquids also usually have a high density. Again, because the particles are close together, liquids have a lot of mass for their volume.
For that volume.
Now, gases have a low density. That's because the particles are very far apart. So gases only have a small mass for their volume.
So interesting, bro.
Now, there are some exceptions to these rules. For example, polystyrene, which we saw earlier. This is a solid, but it has a low density. That's because it has a very open structure and is full of air spaces, so it has a small mass for its volume. I'm showing you polystyrene under a microscope here, and you can see the air spaces. Remember that you'll find plenty of questions on density in my revision workbook, and you can get that by clicking on the link above.
I do not want it.
Okay, so hopefully now you should be able to draw diagrams to model the differences in the arrangement of particles between solids, liquids, and gases. You should then be able to calculate the density of material, and finally you should be able to explain the differences in density between different states of matter.
This takes half an hour recording.
Hi and welcome back to freesciencelessons.co.uk. By the end of this video, you should be able to describe how to determine the densities of regular and irregular solid objects. Now, this is a required practical, and it could come up as an exam question, so it's important that you learn the details. In the last video, we looked at density, and we saw that the density of material tells us the mass for a given volume. We calculate density using this equation. The density equals the mass in kilograms divided by the volume in meters cubed. The unit of density is kilograms per meter cubed. And remember that you're not given this equation in the exam. So in this video, we're looking at how we can determine the density of objects. Now, objects can be divided into two broad categories. Regular objects, such as this cube, have got dimensions which are easy to measure. So we could easily measure the length of each side using a ruler.
For like liquids, they use a eureka thingy.
With irregular objects, such as this vase, we cannot easily measure their dimensions. We're going to look at how to deal with irregular objects later.
By the way, I think I have it.
So let's look at how to determine the density of regular objects, such as the cube. Remember that the density is the mass divided by the volume. So first, we need to determine the mass. We can do that easily by using a balance, such as this one. Imagine that the cube has a mass of 0.5 kilograms.
It's a balance.
Now we need to work out the volume of the cube. To do that, we use a ruler to measure the length of the side like this. The length of each side of this cube is 120 millimeters. In other words, 0.12 meters. The volume equals the length of the side cubed. So 0.12 cubed gives us a volume of 0.001728 meters cubed. Putting the mass and the volume into the equation gives us a density of 289.35 kilograms per meter cubed to 2 decimal places. So as you can see, determining the density of a regular object is relatively straightforward. But what about an irregular object, such as the vase we saw before? In the case of irregular objects, we cannot easily measure the dimensions. Instead, we determine the volume using a method called displacement. So let's look at this now. Just like before, we start by finding the mass of the object using a balance. We then fill a eureka can with water. A eureka can has a spout, so the water can flow out of the can. Now we place the object into the water. This will cause water to be displaced, and it will flow out of the can through the spout.
So cool.
We now measure the volume of water displaced using a measuring cylinder. This volume is the same as the volume of the object. So now we know both the mass of the object and the volume of the object. That means that we can calculate its density. Remember that you'll find plenty of questions on this assessed practical in my revision workbook, and you can get that by clicking on the link above. Okay, so hopefully now you should be able to describe how to determine the densities of regular and irregular solid objects.
Let me, guys, check my second. I need to find my phone. I found it. I've been sent by one.
Hi and welcome back to freesciencelessons.co.uk. By the end of this video, you should be able to describe what's meant by internal energy. You should then be able to describe what happens when a material changes state. We've already looked at the particles in solids, liquids and gases. Remember that the particles in a solid do not move from place to place, but they do vibrate. Particles in a liquid can move around each other, and particles in a gas move extremely rapidly. So what this means is that all of these particles have got kinetic energy. Now, particles also have potential energy. Remember that particles have got forces between them, which are called intermolecular forces. And if they're a molecule, then they also contain chemical bonds. Together, these give the particles potential energy. Now, the internal energy is the energy stored in a system by the particles. It's the total kinetic energy and potential energy of all the particles, and that includes atoms and molecules that make up a system.
That's interesting.
Now, please don't get bogged down by the idea of internal energy. I would recommend, though, that you learn the definition. Okay, now internal energy is really important during changes of state. If we heat a solid, we increase the internal energy. At some point, the solid can turn into a liquid, and we call this melting. If we continue to heat the liquid, again we continue to increase the internal energy, and at some point, the liquid will turn to a gas. We call this boiling.
I'm a physicist when I'm older.
Now, if we cool the gas down again, then we reduce the internal energy. At some point, the gas turns back to a liquid, and we call that condensation.
That's
And
interesting.
if we cool the liquid down further, then we reduce the internal energy even more, and eventually the liquid turns to a solid, and we call that freezing.
That's interesting.
Now, there are a few other points that we need to look at.
Those are the ones which go
Sometimes a
on.
solid can turn directly to a gas. For example, carbon dioxide does that at room temperature and pressure. Scientists call that sublimation, and I'm showing that here. Secondly, remember that when changes of state take place, mass is always conserved. We're not adding or taking away any particles. And lastly, changes of state are physical changes, not chemical changes. That means that if we reverse the change, the material recovers its original properties.
That's true though.
So, for example, if we melt ice to water and then refreeze the water, the ice we make is exactly the same as the ice was at the start. Now, there is one final point which we need to look at, which is evaporation.
Guys.
Now, evaporation is when a liquid turns to a gas, but only on the surface of a liquid.
Surface.
In this case, only the particles on the surface have enough energy to turn into a gas. Remember that you'll find plenty of questions on internal energy and changes of state in my revision workbook, and you can get that by clicking on the link above. Okay, so hopefully now you should be able to describe what's meant by internal energy. You should then be able to describe what happens when a material changes state. Hi and welcome back to freesciencelessons.co.uk. By the end of this video, you should be able to calculate the amount of energy stored in or released from a system as its temperature changes. I'm showing you here some water boiling, and the question is how much energy is stored in hot water? In order to answer that, we need to look at the idea of specific heat capacity. The specific heat capacity of a substance is the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. Now that sounds tricky, but it's actually straightforward. So let's take a look at a sample question. Calculate the energy required to increase the temperature of 2 kilograms of water from 20 degrees Celsius to 100 degrees Celsius. The specific heat capacity of water is 4,200 joules per kilogram per degree Celsius.
Free science lesson.
To answer this question, we've got to use this equation, and you are given this in the exam. The change in thermal energy in joules equals the mass in kilograms multiplied by the specific heat capacity multiplied by the temperature change in degrees Celsius. We've got 2 kilograms of water. The specific heat capacity of water is 4,200 joules per kilogram per degree Celsius, and you will be given that value in the exam. And finally, the temperature change in this case.
Remember this. Mass times specific heat capacity times by temperature change equals the change in thermal energy. And what that means, if you don't remember that, you're going to fail your GCSE.
Is 80 degrees Celsius. Putting these values into the equation gives us a total change in thermal energy of 672,000 joules. We can convert that to kilojoules by dividing by 1,000, giving us 672 kilojoules. Here's a question for you.
So, if you want to take, that's 180. You can times it by 1.5 times that by 9.113. That's gonna be 6.
An iron has an aluminium plate with a mass of 1.5 kilograms. Calculate to 213 joules.
Yo.
Okay, so we've got a 13 joules per kilogram per degree per thousand of 246.5
Yo, I got it
kilojoules.
right.
Here's a final question for you to try. A hot
water bottle, cool. It's with 60 times there will be times it will be the so 60 divided by 7, 5, 6. These numbers divided by 200. Yo.
per kilogram per degree Celsius.
Oh.
Now, to answer this question, you're going to have to rearrange the equation to find the mass.
Interesting.
Pause the video and try this yourself.
Hmm.
Okay, I've rearranged the equation to calculate mass, and here it is. The specific and the mass of specific capacity.
Oh, wait, what? 200 times by 6 is this divided 200. Okay. 200. No. 7,576,000 divided by 200 equals 30. Divided by 500. Listen, how did you get that?
In my Vision workbook. You can get that by clicking on the link above.
You're using the wrong calculator.
You should be able to calculate the amount of energy stored in or released from a system as its temperature changes.
So interesting. And a person joined. Yo, you're so epoch.
Hi and welcome back to freesciencelessons.co.uk. By the end of this video, you should be able to interpret heating and cooling graphs that include change of state.
Yo.
In the last video, we looked at the idea of internal energy. Remember that this is the energy stored inside a system by the particles. This includes the kinetic energy of the particles due to their movement, and also the potential energy of the particles. Now, the potential energy is due to the forces between the particles and also the bonds between atoms in a molecule. So in this video, we're looking at heating and cooling graphs. So let's get started. Imagine I've taken a solid substance and I'm gradually heating it and I'm measuring the temperature. I get a graph like this. Now this is called a heating graph. So we can see that the temperature of the solid is rising as we're increasing the energy of the particles. Now at some point the temperature stops rising and the line becomes horizontal. At this point, the solid is changing state and turning into a liquid. In other words, it's melting. Now, the energy we're putting in is weakening or breaking the forces of attraction between the particles. That's allowing the substance to change state from a solid to a liquid. Scientists call the energy needed for a substance to change state the latent heat. And we're going to look at latent heat in a later video. So during the change of state, we're increasing the internal energy store of the system, but we're not changing the temperature. Now, the temperature that the substance melts at is the melting point, And we can
That's
find that
true,
by
though.
reading it off the graph like this. Eventually, all of the solid will have melted into a liquid, and now the temperature starts to rise again. And again, that's because we're increasing the energy of the particles. Now, at some point, the temperature stops increasing, and the line becomes horizontal again, like this. At this point, the substance is boiling, and again, the energy we're putting in is...
Okay, guys, I'm gonna go for a bit, for like a second. I gotta do something quickly. Yo guys, I'm back. Let me get into my seat. Here we go, guys.
is weakening or breaking the forces of attraction between the particles.
Here we go.
We can find a boiling point from the graph like this. Once all of the liquid is boiled, the temperature starts to rise again.
Dude. It's because they have energy in the
Now,
particles.
if we take a gas and cool it down, we get a graph like this one. This is called a cooling graph. Again, we can see where the changes of state take place. When the gas changes to a liquid, this is called condensation. And when the liquid changes to a solid, this is called freezing. Remember that you'll find plenty of questions on heating and cooling graphs in my revision workbook, and you can get that by clicking on the link above. Okay, so hopefully now you should be able to interpret heating and cooling graphs.
Super interesting.
Hi and welcome back to freesciencelessons.co.uk. By the end of this video, you should be able to describe what's meant by specific latent heat. You should then be able to calculate the energy change taking place when a substance changes state. Now, I need to be honest with you, some of this is pretty tricky. You might need to watch this video a couple of times to get the idea. In the last video, we looked at heating graphs, such as this one. We saw that when we heat a substance, we increase the temperature as we increase the energy of the particles. However, when the substance changes state, for example, melts, the temperature stops increasing and it stays constant. That's because now the energy we're putting in is weakening or breaking the forces of attraction between the particles. Scientists call the energy needed for a substance to change state the latent heat, and we're looking at that in this video. So here's a key definition. The specific latent heat of a substance is the amount of energy required to change the state of 1 kilogram of the substance with no change in temperature. I'm showing you here a block of ice. Now imagine that I wanted to melt 1 kilogram of ice. How much energy would that take? Well, scientists have worked this out. It takes 334,000 joules of energy to melt 1 kilogram of ice. Scientists call this energy the specific latent heat of fusion. So this is the energy required to change 1 kilogram of a substance from a solid to a liquid with no change in temperature. Now, what if we wanted to change a substance from a liquid to a gas, in other words, boil it? How much energy would that take? Well, scientists call this the specific latent heat of vaporization. And here's the definition. The specific latent heat of vaporization is the energy required to change 1 kilogram of a substance from a liquid to a vapor with no change in temperature. Now, we can use the idea of specific latent heat to calculate the energy change when a change of state takes place. We use this equation. The energy for a change of state in joules equals the mass in kilograms multiplied by the specific latent heat. And you will be given this equation in the exam. You'll also be given any values for specific latent heat that you need. Here's a triangle for this equation, but remember that you're not given triangles like this in the exam. Okay, so here's a question for you. Calculate the energy required to convert
specific
grams of ice
0.3 times by 3, 3, 3, 4, 0, 0, 0. 1, 0, 2, 0, 0.
To liquid water. And the specific latent heat of fusion of water is 334,000 joules per kilogram. Pause the video now and try this yourself.
I did, bro.
Okay, so the energy for a change of state equals the mass multiplied by the specific latent heat. In this case, the mass is 0.5 kilograms, and the specific latent heat of fusion of water is 334,000 joules per kilogram. Multiplying these numbers gives us an energy of 167,000 joules.
I thought it was 3. Rookie mistake.
Here's another question for you. Calculate the energy required to convert
0.15. No! Yo. One, 2, 6, 9, 0,
0.15 kilograms of ethanol from a liquid to a vapor. And the specific latent heat of vaporization of ethanol is 846,000 joules per kilogram. So pause the video now and try this yourself.
1, 2, 3, 4.
Okay, so the energy for a change of state is the mass multiplied by the specific latent heat. The mass of ethanol is 0.15 kilograms, and the specific latent heat of vaporization of ethanol is 846,000 joules per kilogram. Putting these numbers into the equation gives us an energy of 126,900 joules. Remember that you'll find plenty of questions on specific latent heat in my Vision workbook, and you can get that by clicking on the link above. Okay, so hopefully now you should be able to describe what's meant by specific latent. Hi and welcome back to freesciencelessons.co.uk. By the end of this video, you should be able to describe how the temperature of a gas is related to the energy of the particles.
That's true.
You should then be able to describe how changing the temperature of a gas changes the pressure. Now, this is a pretty easy topic, so it's a relatively short video. We've already looked at gases in previous videos. Remember that particles in a gas are very far apart and they're in constant random motion. Now, in this video, we're looking at the pressure of gases. The pressure of a gas is due to the particles colliding with the walls of the container that the gas is held in. I'm showing you here a gas held inside a container. By colliding with the walls of the container, the gas particles are exerting a pressure. Now, we can increase the pressure if we increase the number of collisions per second, or if we increase the energy of each collision. And one way to do that is to increase the temperature of the gas.
So cool.
I'm showing you here two containers containing gases at different temperatures.
Because the high temperature has more energy,
now, the first key idea you have to get
the low temperature
is that the temperature of a gas is related to the average kinetic energy of the particles.
Morty every single day.
At low temperatures, particles have got lower kinetic energy. This means there are fewer collisions per second, and these are lower energy collisions. This means that at lower temperatures, the gas pressure is relatively low. At high temperatures, particles have got higher kinetic energy. This means there are more collisions per second, and these are higher energy collisions. So at high temperatures, the gas pressure is relatively high. Remember that you'll find plenty of questions on the pressure of gases in my Vision workbook, and you can get that by clicking on the link above. Okay, so hopefully now you should be able to describe how the temperature of a gas is related to the energy of the particles. You should then be able to describe how changing the temperature of a gas changes the pressure. Hi and welcome back to freesciencelessons.co.uk. By the end of this video, you should be able to describe how the pressure of a gas is related to its volume. You should then be able to calculate changes in the pressure or volume of a gas. And all of this is for triple physics students only. In the last video, we saw that the pressure of a gas is due to the particles colliding with the walls of the container that the gas is held in. Now, the first key fact that you have to understand is that the particle collisions cause a force which acts at right angles to the walls of the gas container. This force, acting over the area of the container, causes the gas pressure. Now, if we take the same gas and increase the volume of the container while keeping the temperature constant, then we reduce the pressure. That's because we've now increased the spacing between the particles. Particles now travel much further before colliding with the walls of the container. This reduces the number of collisions per second between the particles and the walls of the container, and that reduces the pressure. Now, the pressure of a gas is inversely proportional to the volume. In other words, if the volume increases, then the pressure decreases. We can show that using this equation.
True.
The pressure in pascals multiplied by the volume in meters cubed equals a constant. Now, I should point out that this equation is only true if the temperature is kept constant, and you are given this equation in the exam. So let's take a look at what this means. Because the pressure multiplied by the volume is a constant, if we double the pressure, then we must halve the volume. Here's a sample question. A gas has a volume of 2 meters cubed and a pressure of 400,000 pascals. The volume's increased to 6 meters cubed. Calculate the pressure. Pascal. Double the...
Oh, it's times it. We double the pressure and we halve the volume.
Pressure. Then we must halve the volume. Here's a sample question. A gas has a volume of 2 meters cubed and a pressure of 400,000 pascals. The volume's increased to 6 meters cubed. Calculate the constant. A gas has a volume of 2 meters cubed and a pressure of 400,000 pascals. The volume's increased to 6 meters cubed. Calculate the pressure. Okay, so we can see that the volume of the gas has increased by 3 times, from 2 meters cubed to 6 meters cubed. That means that the pressure of the gas must have decreased by 3 times, from 400,000 pascals to 133,333 pascals. And that's our final answer. Here's a question for you to try.
This could be easy. You divide it by 5, it'd be 10,000, right?
A gas has a volume of 10 meters cubed and a pressure of the pressure. Okay, we can see that the volume of the gas has increased by 5 times, from 10 times, from 50. Here's a final question for you. A gas has a volume of 5 meters cubed and a pressure of 150,000 pascals. The pressure decreases to 50,000 pascals. Calculate the volume.
Three. It's divided by 3. So 3. 3 times 5 equals 15.
So pause the video and try this yourself.
5 times 3.
Okay, we can see that the pressure of the gas has decreased by 3 times, from 150,000 pascals to 50,000 pascals. That means that the volume of the gas must have increased by 3 times, from 5 meters cubed to 15 meters cubed. And that's our final answer.
True.
Remember, you'll find plenty of questions on gas pressure in my revision workbook, and you can get that by clicking on the link above. Okay, so hopefully now you should be able to describe how the pressure of a gas is related to its volume.
True. Free science lessons.
Hi and welcome back to freesciencelessons.co.uk. By the the end of this video, you should be able to describe the effect of doing work on an enclosed gas. This is for triple physics higher students only. I'm showing you here a gas inside a piston, for example, a bicycle pump. As we said in a previous video, the gas particles colliding with the walls of the container apply a force at right angles to the walls of the container, and this causes the gas pressure. Now imagine that we compress the gas by applying a force on the piston like this. We've now carried out work on the gas. We're going to look at work in more detail in the topic on forces. Now, work is defined as the transfer of energy by a force. So because we applied a force to the gas, we've transferred energy to the gas particles. What this means is that we've increased the internal energy of the gas. Now remember that the internal energy includes both the kinetic energy and the potential energy of the gas particles. And we saw in a previous video that the temperature of a gas is related to the average kinetic energy of the particles. So because we've increased the kinetic energy of the gas particles, we've increased the temperature of the gas. Now a good example of this is a bicycle pump such as this one. These pumps can get warm when we use them to inflate a tyre. And again, that's because we're doing work on the gas, increasing its internal energy. Remember, you'll find plenty of questions on work done on gases in my Vision workbook, and you can get that by clicking on the link above.
That was
Okay,
the
so hopefully
video,
now
guys.
you should be able to describe the effect of doing work on an enclosed gas.
Vision, guys. I hope you had, yo, guys. It's been your boy, Bumble J, Storm the boy, Bumble JPC, you know, the boy. And this has been my reaction to physics vision. These next